So welcome everyone to the series of talk in the Northwest Database Society, the second for today. It is my great pleasure to introduce Holger Pirk. Holger, he received his master's from Humboldt University, then got his PhD also in Amsterdam with Martin Kersten and Stefan Manigold. Then he spent a postdoc at MIT. He joined last year as a lecturer at the Imperial College of London. And Holger is interested in the interface between hardware and database systems. So today he's going to talk about his project in this space.
Okay, thank you. Yeah, thanks everybody for being here. So, right, the title of the talk is Hardware-Conscious Data Processing Systems. But in the end, like, you know, this is kind of code, right? Like, in the end, it's not about hardware, it's about performance. And I found like the best way to study performance is always in the context of a case study. And so we've done this like kind of off-the-envelope case study. And so what we thought about was basically like analytical queries, right? Like something like, oh, how did our sales develop in the United States in the last couple of months? And something you would express in SQL like this, right? Like select all records, country equals the United States, group them by month, and aggregate the results. And this is like, you know, we have this benchmark for this, right? The TPC-H benchmark, and this is roughly equivalent to the first query of that benchmark. And so what we've done is we've taken the TPC-H data generator and generated roughly 10 gigabytes worth of data and loaded this into what is arguably the most common database system out there, which we felt was Postgres, and executed the first of the benchmark on like a $5,000-ish machine. So it's like a decent workstation machine. And you run this query, and it runs in about 100 seconds. And okay, so now 100 seconds is just a number, right? Like without context, it's really hard to say how good or bad is that number. And so what we've done is said, okay, look, we know this is 10 gigabytes worth of data. So it's perfectly feasible to keep this all in main memory. So let's do exactly that. Like let's create a RAM disk. Oh, sorry. This is, by the way, this is a lower bound. Sorry, I got confused here. So if we keep all of that data in main memory, we can establish a lower bound on how fast this query could possibly run by just dividing the data set by the memory bandwidth. And that lower bound is 37 milliseconds. So it's like, you know, more than 3 orders of magnitude from the actual performance that we got from Postgres. And so then the question is, right, okay, yeah, Postgres is a disk-based system, so is that the problem? Is the disk the problem? Is the solution maybe just main memory resident data? And so for that is what we have done is basically said, okay, we want to eliminate disk as a factor. So let's take the database, put it on a RAM disk, increase Postgres internal buffers to virtually infinite, and rerun the same query. And now I'm curious, like, you know, if you want to venture, like, you know, let's say Postgres, no disk on RAM disk, what do you think the performance is going to be? Like, is it like...
You're not including the disk access time.
Exactly.
After I've loaded it onto the disk.
Yeah. Okay. It's all like, you know, these are actually hot runs. So any guesses?
3 seconds.
Yeah. It's really depressing, right? So there's like virtually no impact that the backend has on the performance here. But there are systems, and there is this.
Isn't that awesome? Isn't that awesome? You said it's depressing, but isn't it awesome that it's?
Well, it might be awesome if you ignore this bar, right? But like let's look at other bars, right? The question now is, so I mean, it's awesome if you care about robustness. Like there are aspects in which it is awesome, but there are aspects in which it is very depressing, right? I don't know which.
But the optimistic perspective is that if you had shown us the RAM, you know, the in-memory performance first, and then you said how much worse if we have the data on disk and not use all that memory, it's actually not that bad.
That is true. And that all holds for Postgres, right? So let me show you the rest of the bars, and then let's discuss this further. Because there are these systems, and MonetDB is this system, right, that was developed at CWI in Amsterdam, optimized for main memory access. And that runs the same query around 30 times faster. And then there's the system that we've built, like during my time at MIT, this Voodoo system, which runs, again, the same query another 20 times faster. So there are, like, you know, orders of magnitude left there. And so let's, again, like, you know, how awesome is that if I put that next to it, right? There's clearly something to be done there. And so like what I want to talk about is how did we get there, right? What is it that you need to do to go from that to that? And like, I mean, the first obvious thing to do is like, okay, so let's analyze what Monet has done, what makes Monet different. And what they do is this idea of column at a time processing, right? And to explain this, I want to briefly, you know, show like here is a database architecture diagram, right? Like most of your databases look like something like this. You have some declarative interface on top, and from that you generate some kind of logical plan, and that usually contains things like an algebraic description of your operator, selections, joins, group bys, and you apply some optimization to that plan. And from that you generate a physical plan. So basically just implementations of these logical operators. A table scan implements a select, a hash join could be an implementation or is an implementation of a join. You apply more optimization, and then you have the database kernel. And this database kernel is, I mean, in the end, it's just a library of functions that we use to implement the physical plan operators, right? So I've like, you know, basically put the header here of a scan function, which could be an implementation of a table scan. And so what's the difference between Monet and Postgres in that light? Well, Postgres is what we call a tuple at a time kernel, right? So that means each of these kernel functions processes exactly one tuple. And that leads to very high interpretation overhead, because if you know nothing else about computer architecture, you know that function calls are expensive, right? And it is also hard to parallelize. So there are like entire papers about like, you know, how to parallelize plans in Postgres. And if you put these two together, that not exhaustively, but to a large extent explains why the RAM disk has so little impact, because there's so much performance lost in the kernel. And so what Monet does is this idea of column at a time processing, right? So what it does is in every single function call, kernel call, it processes an entire column worth of data. And that means that the overhead is still there, the function call overhead, but it is amortized over many tuples or values. And it is also relatively easy to parallelize because every operator can partition its input independently of everything else. Trivial. Okay, cool. So back to our study. This basically accounts for this 30x performance overhead here. And so now the interesting thing is, what did we do to improve on that? And the main idea that we have, or that we've done here, is we want to generate code, executable x86 code instructions. And not just any kind of code, but optimal code for a given hardware architecture. And so for that, I want to briefly introduce this idea of query compilers that is quite hot right now. And it's been pioneered by these people in Munich, the Technical University, Thomas Neumann and his group. And the main idea is like we go from a logical plan to an executable program. And they've had a VLDB paper a couple of years ago, which describes a very nice and elegant way of doing this. So what they do is they start with a plan that looks something like this, right? It's a bit more complicated. And then they traverse this plan left deep first, and they generate a program from that. And they generate LLVM code, but for illustration purposes, I want to generate Python code here. And so what they do is they traverse this plan, and every time they encounter an operator, they emit a piece of code from a template database. So say in the case of a join, this is a hash join. The first time I encounter this operator, I need to build a hash table. And so the piece of code that does that in Python looks like this. And what it does is read the input, calculate a hash for every tuple, and then insert the value into a hash table. And when I continue traversing that plan, here we go, and encounter the join operator for the second time, now I need to probe that hash table. And so here's the piece of code for that. Read the input, calculate a hash, and then probe the table. And you continue traversing the plan like this and successively build up a program. And it's not super important that you'd be able to recreate that program. But what I would like you to believe is that if I gave this query to a reasonably smart undergraduate student and asked them to implement it in Python, the result would probably look a lot like what you see on the right. It's not like, you know, particularly tuned or optimal, but like it does the right thing, and it's pretty good code. And we actually found that you get about a 4x performance improvement for the TPC-H query 1 case that we had earlier from just generating naive code. It's not the 20x that we want to achieve, but it's something. The more interesting thing is what this does to the database architecture, because it basically removes this layer here, right? I said that we're going directly from the logical plan to an executable. So it also removes the database kernel and now goes directly from logical plan to this executable. And so now you might look at this and say, hey, great, I've just, yes?
In the physical plan, you still need to make a decision whether you're doing a merge join or a hash join or an index join. So did you take this out of the picture? Or?
Yes. And this is, oh, no, wait, I didn't. They did. Like out of the conceptual picture. So in Hyper, they don't actually make that decision. They do hash joins only. And so they basically make that decision when they build the system, when they build the query compiler. And so basically made this decision way, way, way before any of this happens.
Again, that's sort of the same question, though. Your assertion is that it changes the architecture. That's what I would sort of challenge. There's no reason why you couldn't have that physical design decision in there.
Yes, wait a couple of slides. That's basically what I'm getting to. Yes, you lose basically exactly that problem, right? You lose this degree of freedom, or you move that decision to the development of the database, which makes it really rigid and inflexible, right? Like, you know, it turns out sometimes a sort merge join is a really good idea, and like, you know, Hyper just doesn't implement it, like until. Yeah. It's a similar.
You can generate a cross product if you choose your order poorly, right? So which would be.
Yeah. Yeah, so like this physical player clearly adds something, but like let's get to that again in a couple of minutes. But I think this does something even worse, right? Like, so you could look at this and say, oh, cool, I've removed the box. I've made things simpler, right? Like the architecture is simpler now. But other than like losing the functionality that was in that box, I've also now introduced this this boundary here, right? But because before all of this was data management system, now this part is compilers. And like they use LLVM as a framework there. And the data management system part is still on top. So I've strictly made things worse, right? Like, because now I have like 3 different realms of computer science I have to deal with. And that compiler usually has a set of optimizers on its own. So basically, if I want to build, like, want to generate an optimal program for this, I need to, at the very least, know something about compilers and data management, right? And so now I've basically restricted the subset of people that can do this, well, by quite a bit. And this is just to generate like a simple program, right? As I said, this is your smart undergrad program. If you want to write like a really good program or generate that, you also need to take things like computer architecture into account, right? What is like the cache sizes? What is like, you know, cost for branch prediction, stuff like this. And like basically integrate all that knowledge that is being generated there into that small bubble. And like when preparing this, I've started looking into, well, how much knowledge is there really in computer that falls in that bubble? And I started creating a list of like the last 10 years worth of VLDB and Sigmod papers of like what, like, you know, the techniques we could integrate there, and eventually ran out of steam. But like there's basically entire groups, and like I'm certainly guilty of doing that myself, because, you know, it turns out this is actually fun and interesting. But we are generating like a deluge of new optimization techniques. And so for illustration, let's just take 2 of these that are arguably among the simpler ones, the straightforward ones that, you know, if you're smart undergrad wants to try out things would probably start with. And those are Multicore parallelism and SIMD parallelism. And let's take a very simple query, okay? Like very, very like base version, like just sum up the values in a table of a single attribute. And how multicore parallelism works, or how you would usually implement this, is by just partitioning your data into consecutive regions. So say I want to, like, you know, parallelize this 4 ways. I would generate 4 color-coded, in this case, color-coded partitions, and then calculate a sum for each of them, and then calculate a global sum in the end. And you can do a similar thing using this idea of single instruction multiple data parallelism. And this is something that virtually every CPU has these instructions now that I briefly want to explain here. So the idea is that usually when you add have an add instruction in a CPU, it takes like a 1 input value and a 2nd input value, and it generates a sum. And the only difference that SIMD now makes is it does the same thing to, like, say, 4 input values and 4 second input values at the same time in a single instruction. And the nice thing about this is we can actually use this to basically partition our data in a slightly different way. And now, like, the fact that the colors are not very visible actually becomes a problem. But basically, we add up all the values in the say let's take the orange one. All the orange values get added up using SIMD instructions. And okay, so this is conceptually very similar, right? It's just different ways of partitioning the data. And what we've done, and we've actually put this in the paper, is we have implemented this using like probably among the most common frameworks that you use for parallel programming in C++, using for multicore parallelism, Intel's threading building blocks library, and for SIMD, your compiler has something called intrinsics, basically operations that, like, an abstraction over these vectorized instructions. And we've compared these two programs. So these are the two programs, and I'm not going to walk you through the program, but what I want to point out that the only line that is shared among these two is the first one, which is load the input. And this is just something like conceptually similar things look completely different in the low-level implementation. And this isn't just syntactic. We've actually looked at the concepts from the documentation of these frameworks, and it turns out that they're using completely different concepts to express this. What TBB is largely built around like lambda functions, so it's like a functional abstraction, whereas SIMD is very C++ heavy, where you cast objects into SIMD types and operate with those. And so this is annoying, right? And this gets even worse because what we also want to do is we want to still implement the classic database things like join ordering. And if we think about where to place all of these optimizations in the database architecture, they actually end up in different not just different components of the database, but different realms of computer science, right? Operating systems, compilers, and data management systems. And this is like, again, like we're shrinking the number of people that can work with this like to basically 4 guys. Or girls, and this is one problem, and the other is these two optimizers. Because the database optimizer usually knows a lot about the data, right? It has histograms, it might have like information about correlation of attributes, but it knows very little about the hardware. Whereas your compiler optimizer usually knows a lot about the hardware because that's what it's generating code for, but knows very little about the data. And so the question we asked ourselves was, well, what if we had some kind of like unified intermediate layer that all of these optimizations could be mapped to, and a single optimizer that is both hardware and data aware? And that is basically the vision behind this Voodoo project. And so I want to talk about 3 aspects of Voodoo. First, I want to briefly introduce what Voodoo looks like, what it is. And conceptually, it's a vector algebra. And then I want to talk about like what you can do with Voodoo. And first, you can build a high-performance database kernel that is portable to different hardware architectures. But I think even more interesting, and this is the part that I'm most excited about, is it's a platform for database performance engineering. And there's actually like a decent amount of connection to like Stratos talk earlier. And like, we have slightly different approaches to this, but it makes it interesting. Okay, so the Voodoo vector algebra. So we had 3 design goals when developing Voodoo. First, we wanted to be as fast and as expressive as C, because nobody's going to pick up our solution if they pay a performance overhead or they can't implement like that crazy new algorithm that they have in mind. We wanted to be optimizable like relational algebra, because that's actually really nice, right? Like the algebraic properties of relational algebra means that optimizers can just like do local changes to the plan and like, converge to a different part of the plan space. And we wanted to be portable to different devices, because this heterogeneity, CPUs, GPUs, FPGAs, is very much part of performance engineering in the time that we live in. And then the last thing is something we never really developed for, but it just happened, and I think it's probably the coolest thing about it, is I think Voodoo enables the serendipitous discovery of new optimizations. And I have an example of like how this worked out for us towards the very end. Okay, so let's briefly talk about like how we achieve these goals. So first, fast and expressive SC. So okay, sure, we want a fast compiler backend. Okay, those exist, like, that's not really a big challenge. But what is important is we want all tuning decisions to be explicit in the program. So I should be able to look at a plan and tell exactly what this does, even estimate its cost. That's, yeah, basically a guiding principle there. That being said, it's still focused on data processing, which roughly translates into not Turing complete. So we don't have an iterator operator. It's still a data flow language. And that ties into the second goal. Because we want it to be optimizable like relational algebra, all plans are basically data flow programs. And that means, yeah, optimizations are just graph transformation rules, which is nice. Yes?
To be as fast and expressive as C. Mm-hmm. If that's your goal, why can't you then replace C? So isn't that a goal that's not achievable, because then you would essentially have C, and you would say, well, all the people who have built compilers in the past, they're not really good because they haven't been able to do the optimization.
That is a good point. You could probably do this. There are a couple of reasons why you wouldn't want that necessarily. First is this focus on data processing thing, right? So since a typical thing, for example, is we've tried implementing, or we have implemented PageRank in Voodoo. And there you have to test for convergence and then, like, you know, run a number of iterations based on that convergence test. We can't actually do that in Voodoo right now. We have to do the test outside of Voodoo because we don't support iteration. And we can't run loops. And so, like, you know, it isn't, this is what I mean by not Turing complete. We can't do everything that C does. We can do everything, or I claim that anything you would need in a relational database, and maybe even, like, you know, a large part of the program space around it, you can do in Voodoo, but again, focus on data processing, right? There are other problems, like Voodoo is actually quite verbose. Often you don't actually want to tune every single knob, right? This is something that is great for a machine or a performance engineer or a nerd like myself. I'm happy, like, you know, tuning everything, but a lot of people prefer higher level languages, right? And I would, funnily enough, consider C, or at least C++, a higher level language in many respects. So, okay, but I'll just move on. Like, you know, I'm happy to, like, you know, discuss this further later. Okay, and then the second thing is we want, like, right, so to make it optimizable, we need a sound definition of all operators, right? The semantics need to be clear so I can reason about it and, like, you know, actually reason about, like, is the transformation I've just applied correct? And then, like, the last thing is this portability to different devices. And for that, we basically had to resort to the least common denominator, both in terms of data model as well as operator set. And let's just, like, you know, briefly talk about what that means. So our data model is basically a very thin layer of abstraction over what I would call integer addressable memory. So just like virtually every device you work with has some form of, you supply an address, you get a value back. Or you write to an address and then you read the value and you hopefully get the same value back again. And in C++, the abstraction over this is just an array of structs. If you're more like a higher level person, it's an ordered collection of tuples that all share the same schema. So very simple, and basically every device has that. The more interesting thing are the operators, because in Voodoo, all operators are parallel, but some are what we call controlled. And let's talk about the parallel ones first. So those are basically like what we call embarrassingly parallel, right? Arithmetic operations, logical operations, bits, projections. We have something that is a gather, which is basically the vectorized equivalent of an array lookup. Provide a value vector, a value of positions, resolve the positions into the value vector. It's basically that. And right, the more interesting ones are the controlled operators. And they're all, or most of them are called fold, select, fold, scan, fold, max, fold something. And so to explain this, I want to briefly revise what a fold is for those who had their undergrad days, like, you know, a little bit longer ago. So the main idea is a fold operator is an operator that accepts a sequence of values in addition to a binary function defined on the elements. And so what it does is applies the binary function to the first two elements of that sequence, and then takes the output of that and combines it with a third element, and the output with that with a fourth, and so forth. And it builds an evaluation tree that looks like this. And you can, like, by looking at this tree, you see this is an inherently sequential operation. All these data dependencies that are being carried.
Generalization of what we would call a scan.
A scan as in a prefix scan? Yeah. Yes, it's basically, yeah. I think that's correct. And right, okay, but there's an interesting aspect to your question, like because but okay, let's move on to the extension we did. And so because this is an inherently sequential operation and we want our operations to be parallel, what we've done is we've slightly extended the definition of a fold. And so what we've done is we've said, okay, in addition to a sequence of values, we also get a sequence of partition IDs, or what we call a control vector. And so what we do is we traverse these two basically in lockstep, and as long as we find equal values in the control vector, we fold into the same output. So you can see always this is all being folded into this output. And when we find a value that is unequal to the previous one, we start a new fold, a new output, and then we traverse that one and continue traversing it. And that way, we can basically logically partition our input by supplying something that is essentially a sequence of data values, which is like, I think it's a very databasey thing. We're using something that isn't really data, but looks like data for like, control aspects. And if you want to, for example, do this example I had in the very beginning about like aggregating all the values in a table, you can basically run a fold sum with a control vector that looks like the one on top, and then run a second fold sum with a single control vector. It's just a value, a range, a sequence of identical values that then folds up all the values. And the nice thing about this is these control vectors, we put them in the program as tuning hints, but they actually get removed at compile time. So there's like no runtime overhead involved with these. Okay, cool. So, but now the question is like, how do we generate these control vectors? And to do that, like, let's start with the multicore part first. So what we have is a range operator. It just enumerates all the tuples in an input vector, 0, 1, 2, all the way to the length of the vector. And we have an operator that just generates a constant run of values. And if we integer divide the first by the second, we generate this control vector that looks exactly like the control vector that we've just used to express multicore partitioning, multicore parallelism. Okay, I think I have an example of what the program looks like exactly here. So this is the Voodoo program that implements the same thing that like I've had in the C version before. And I don't want to walk you through this, but what I want to show is this pattern here. Range operator, a constant, and then an integer divide. That is basically how we assign partition IDs to our tuples. Okay, great. So far, I've made things different, but not necessarily better. And now I want to convince you that this is actually better. And for that, let's go back to the other implementation that we have, the SIMD implementation, which, as I said, was just a different way of partitioning our data. So instead of having like all zeros in the beginning and then all ones, what we have is 0, 1, 0, 1, 0, 1, and meaning that all the white values here get folded into the first output element and all the gray ones into the second. So how do we create a control vector for that? Well, we again start with a range. We have a constant. In this case, we generate a 2. And if we modulo divide the first by the second, we actually generate exactly the pattern that I've just used to express SIMD parallel processing. And the neat thing about this is that now, if we compare these two programs, right, this is the multicore parallel version, this is the SIMD parallel version, the only difference is this operator here, right, a divide versus a modulo plus a constant that is actually the tuning parameter here, the number of lanes versus the size of a partition. And with some very, like, I'm calling it simple static analysis, but it's super crude. Like, it's very easy to write a backend that actually maps this to the appropriate implementation. And so, like, static analysis is already, like, sounding a lot grander than it is. But, like, with very simple analysis, we can then map this back to the appropriate hardware architecture. Cool. So what can we do with this? Well, first, we build a high-performance database kernel. And so this is what the Voodoo processing system looks like. And I've basically, like, replaced this unified algebra with a Voodoo box, and we're building on OpenCL as a backend. And yeah, well, we've had an LLVM backend for a while, but that actually turned out to not have a lot of performance improvement. Okay, good. Okay, cool. So let's briefly walk you through how we generate these plans now. And for that, let's complicate the query a little bit. Now we're not just summing up the values, we're also applying a predicate. And we're actually starting from relational algebra. Funnily enough, we're using MonetDB's query compiler, so we're kind of hooking under Monet. And from that, we generate a Voodoo plan. And from now, I'm going to stop using this textual representation and switch to a graphical one. And to also demonstrate, look, this is a data flow language, right? And so how do we generate the the plan for this? Well, we basically do what the hyper folks did, the guys in Munich. We traverse the plan left deep first, and every time we encounter an operator, we emit a piece of code. So for example, when we encounter the line item scan operator here, well, we actually only have to scan the ship date column first. So we just emit a piece of code like, okay, access the ship date column here. Then we continue traversing. We encounter the select operator, and that was is greater than a constant, right? So here's the constant operator, greater. And then there's a fold select here. And that one produces output positions of qualifying tuples. So yeah, basically every tuple that qualifies has its position flowing out of this operator. And then we can use, when we aggregate them, use a gather to read like the values from a second column and then fold them into a global constant. And actually I can see here, this is the control vector for this fold sum. And this is a constant, which tells me, oh, this is a single-threaded program. Because I know this is a single run of equal values. This means this is not partitioned, a single threaded program. This is what I meant by I should be able to look at a plan and tell you what it does. Okay, cool. So from that, we can then generate the undergraduate C version by basically, again, traversing the query plan, in this case, in dependency order, and emitting pieces of code. So for example, when we have a scan node, we just emit an empty loop over the tuples in that relation. Then here we apply a predicate. Okay, that becomes the body of the loop. Then we have this fold select here, which just translates into an if statement around the predicate. In the body, we first read the values, the quantity column, using the iterator, and then sum them up. And again, like it's not super important that you'd be able to recreate this, but this is like, you know, a pretty decent implementation of this query. And if we want to do the graduate version of that program, now we want to, you know, multicore parallelize this. We just introduced this new piece here, which is this pattern, right? You've seen this range, constant divide, plus a fold sum. So this is basically a per partition aggregation, and then a global fold sum in the end. And Voodoo is smart enough to figure out that these two vectors have different these two operators have different degrees of parallelism, and that it needs to materialize intermediate results here.
I just want to make sure that I understand. So there is a difference in the logical plan between targeting a SIMD architecture or targeting a multi-core architecture.
Well, I would consider this a physical plan. I would I mean, this distinction there is somewhat fluent, right, between like a logical. But yes, here, you know, in this case, yes, if we're targeting these two different architectures, that will be visible in the plan. Yes. Mm-hmm. Yep. Okay, cool. So we built the system around this, and well, first thing we compared against was this MonetDB system, and this is TPC-H queries, scale factor 10, and we're basically beating the crap out of MonetDB. I mean, like every single query we're performing like lots better. But this is also not that surprising because MonetDB doesn't generate code, right? It materializes all its intermediate results. And so this isn't really a fair comparison. Like the architecture is just very different. But what's interesting here is like query 1 is this old acquaintance of ours, right? That was the initial query we started with. More interestingly is this hyper comparison to hyper. And because hyper also does code generation, but it implements this going from logical to executable in one giant leap. And the picture here is a bit more nuanced, and it's exactly what we expected. Generally, we're competitive. So if we look at like most of the queries, we'd say, yeah, performance is like, you know, in the same ballpark, which tells me, okay, we're not adding a lot of overhead here. But in some queries, like TPC-H query 1, for example, there's not really much to optimize. It's a single scan. If you pick like a reasonably sane order in which you apply the predicates, we're like, you know, there's basically nothing to optimize, and that's what we're doing, like roughly the same as hyper. There are other queries, like the ones I've marked here, where we're like sometimes outperforming hyper by like 5 to 6x, and those are the ones where there's actual physical design decisions to be made. And there we can, like, you know, in Voodoo represent these, whereas the hyper people would basically have to go back to the drawing board and re-implement this. They could do this, but it will take them a month to do it. And so this is basically why I would say, like, this is the advantage. There are actually some queries where we're slower. I'm happy to talk about those. Those are top-end queries. We have a Sigmund paper earlier this year basically fixing this problem. So that's interesting too. Okay, but now the last thing, I'll try to, you know, speed up. How to use Voodoo as a tuning tool. And for that, I want to complicate our query for a last time, and we want to do what I would call selective foreign key joins. So in plain English, what we want to do is like select all items that were sold at a discount greater than X. So apply some predicate. Then look up their price from a different table. So that's a join, and then sum them up. So in SQL, this looks like this. Again, executed on the TPC-H schema. And you can see here, like, we have two relations, so we're performing a join. This is 10. But it, actually, in this case, it doesn't really, for this, it doesn't matter. Right, so what is interesting about this query is that the join isn't actually a general join. This is a primary key foreign key join, right? Because the condition is defined in the schema. And that means, yeah, we find exactly one join partner in the parts table. And that means every database worth its salt will build a foreign key index. So certainly Monet does this, Voodoo does this. So basically it's a surrogate column, a column that's hidden behind that just contains pointers to the matching tuples in the parts table. Okay, there's not like too much to see here. But the interesting thing, what we can do to evaluate this query now is apply the selection on the discount column, right, greater than whatever, say 0.05. For the qualifying values, we read the pointer, pointer to the matching tuple, and then resolve that pointer and read the price column, and then do the aggregation. Okay, cool. So what's interesting about this query? Let's forget the fact that we have to apply this predicate here. Let's just remember some queries, some tuples qualify, some don't, and these should be red and green. But okay, some qualify, some don't. And now let's think about which values are being accessed, like which memory access do we have to perform to evaluate this query. And let's see, yeah, good, this is visible. So obviously I have to scan the discount column, right? I have to apply this predicate to every single value here, but only for the tuples that qualify, the green ones here, do I have to read the part key column and resolve the pointer into the price table. And there's some values here that are never accessed, and there may even be some values here that are never accessed because no qualifying tuple is actually referencing this entry in the price column. Okay, cool. So I can take this query, I can generate a Voodoo plan from this. The plan looks like this. From that, I can generate a C program. And here you find the components of this, right? Like here's the selection implemented. Here is the read the pointer part. And then here is resolve the pointer and do the aggregation. So now the interesting thing is the performance. And we would expect the most important performance factor here is the selectivity of this predicate, right? And so now let's think about what we expect with increasing selectivity, what the performance looks like. We would expect something like this, right? Because the more tuples qualify, the more work, strictly more work I have to do. Read more values, do more aggregations. But it doesn't look like that at all, right? In practice, it looks like this. And the interesting fact here is that this is due to the way the CPU evaluates this loop, because it speculates when running one iteration, it already speculates about the next one and speculatively executes the next iteration. And if it makes a mistake, then it has to roll that back, and there's overhead involved in that. And that's actually most critical, around 50%, because that's when it's hardest to speculate. That's basically when it flips a coin. Okay, so this is a well-known problem. There's actually a solution to this. And that solution, well, most people tend to call it predication, but Ken Ross, who came up with this, hates us calling it that. But he doesn't really have a better term for it, so I'll just call it predication. And the idea is basically to replace that if branch with an arithmetic expression. So what we do is now we read this value and we evaluate the predicate and multiply it with the value that we've just read. And so what happens here is if this predicate is false, this part will evaluate to 0, and the multiplication result will just be a 0, and we'll add a 0, which is a no-op. If that predicate is true, this will be a 1. The multiplication will do nothing, and we've added the correct value again. And this removes the speculation overhead. I can do this in Voodoo by just removing the fold select and having a multiplication here and generating a new plan.
Compilers can do the optimization automatically.
No, they don't. Actually, no compiler, because I will tell you why in 2 slides. So why is this? Actually, no, in one slide. Because what does this do? It changes the memory access pattern, right? Because now, before we could skip these values. But now each of these values partakes in the multiplication. So that means these values, even though they never qualified, will still have to be accessed, right? And so you're trading in a better branch prediction behavior for memory access. And generally, memory access is considered, I think, worse than branch mispredictions. But there's actually like a performance trade-off here. So I think most compilers don't use. They have something called conditional moves, which they often use instead. But okay, let's look at the performance, because that's actually interesting here. So yeah, we can do this optimization in Voodoo, right? Like this is what the generated C code looks like. And the performance looks like this. Now it's super stable, right? Because we're always doing the exact same amount of work. But in the cases where branch misprediction was a serious problem, we've improved things. In the cases when we had very few memory access, we've actually made things worse. And I think this is why most compilers don't. And maybe with PGO they do. Okay, cool. But now here's the cool thing about Voodoo. So if we reason, now we have this like, very a sound definition of each of these operators. And now we can actually reason about new plans that we can do. And it actually turns out there is an equivalent plan here that replicates the multiplication through the gather. And so what this does, like the plan now looks like this. And why is this correct? Why can I do this? Well, what does this do? So before, I had to access all values. And so what I do now is I take all the values, all the tuples where this didn't qualify, take their pointers, which are marked in red here, and multiply these with the outcome of the predicate. Which means if the predicate was 0, I'm actually redirecting these pointers to the first item, right? Because now I'm multiplying the value here, but the pointer. And that basically means that every time a value isn't accessed, I'm accessing the first value in the price column instead. Which now you might think, well, okay, but I'm still doing the same amount of work. But this item will now be super hot in cache. And so I've basically combined the good branching behavior of the branch-free solution with the good memory access behavior of the branching solution.
So what you just showed, like exactly this, and what you have on the previous slide, that really seems to be kind of the crux of what makes your system so interesting, right? Because if I take a system like Hyper and they go from logical pre-plan directly to generating code, we can say, well, I can improve that system by going from logical to still doing a physical pre-plan, all of these optimizations, but then from the physical plan, taking that whole thing and generating more efficient code.
Yes.
But in your case, because we have this lower level algebra with these smaller primitives, then you can say, I can actually, once I I'm ready to generate, I can do a lot of these tiny level reorderings that I wouldn't be able to do otherwise.
Exactly, exactly. So in that way, like I think there's actually like, I'm kind of touching upon Strato's work as well, right? Because this is something like, I would say that, can I do this in C? Yes. Like, I've actually, like here is how you do the same thing in C++, right? You just replicate the predicate inside this. But it's harder to see. And like I actually, when developing this, I only like recognize, oh wait, this is a point in the design space when looking at the Voodoo representation, because we've removed all the syntactic overhead that comes with C, all this like problem around it. And like just to demonstrate why this is good, right? Like now I've basically created this green curve, which, as I said, like combines the best properties of both of the other solutions. And I think this is really the core of what makes Voodoo cool, I think. It's not just a system that, like, is a high-performance database system, but it actually, I would say it's a system that makes you smarter, right? It makes you see points in the design space that were hard to see in languages like C++. And that's also what I meant in the very beginning when I said that this enabled serendipitous discovery of new optimizations. So technically, I'm done. I have some slides on future work, but I'm also already 12 minutes over time. Okay, cool. Yeah, thanks so much.
Let's take one question or two. Yes, please.
Yeah, it's very interesting work. So one of the things that we've been noticing, so at MCCO we've been slowly moving away from actually compiled execution in favor of interpreted execution with well, interpreter plus vectorized execution. We've been seeing actually performance. We're comparing with the numbers from the Voodoo paper. We've been seeing about 4 times faster. And the approach was to, I mean, there's still a lot of optimization that this type of system leaves on the table versus actually building a system of composed primitives, each of them optimized. Like, for example, one of the optimization that I mean, the usage of SIMD that you have is rather limited, right? It's the naive SIMD usage rather than more creative things that you could do. So what, like, do you think, yeah, so basically, do you think that this type of approach is where the rest of the industry should go? Do you think, yeah, basically, what are your thoughts? Even Hyper is slowly moving away from compiled execution. It has been adding kind of more interpreter. So what are your thoughts?
Okay. Okay, there are a lot of layers in this question. So I would say one thing is, should everybody build, like, you know, their system on an abstraction like Voodoo? I think it depends, right? Like, very much like the way Stratus sees this as well, right? Like, this is as a tool that is supposed to guide you towards, like, you know, new optimizations. You would still likely implement them in, like, you know, whatever language your system is implemented in. And so I would say, like, introducing new abstractions, you better have a reason for doing it. And I think the reason in our case was to enable this design space exploration. And so that, I think, is a good reason. But once you have found your new point in your design space, your new implementation, probably implement it, like, you know, into whatever abstraction your system already provides. I'm not sure you would want to, like, you know, build something into that. The second part of your question, or the first part actually, about, like, so the question is, can you express your optimizations in Voodoo? And if so, then we can take that and, like, fold it into the rest of the executed program, right? So I would say, if you have a low-level optimization that yields good benefits in an interpreted fashion, it will probably also yield good benefits in our solution, right? And we can add that extra bit of good optimized, like, inline code. And so I know what paper you're referring to. I haven't gone, like, you know, actually looking at implementing this in Voodoo. But if it isn't implementable in Voodoo, that's a problem, and I will definitely look into that. I would hope that it should be implementable.
Okay, we are running out of time.
All right.
I suggest you thank Holger and we get questions.
Yeah, thank you.